Hello, I am Ehsan Jafari, an expert in membrane technology. Before we start learning this lecture, just a quick note. I am available for your private consulting, system design, troubleshooting, and procurement. If you need professional support for your business, just hit me up on WhatsApp. Now let's begin the tutorial.
Hello everybody and welcome to this presentation. After a description of general concepts before the design, we continue the membrane design in this lecture with reverse osmosis and nanofiltration design in 10 steps. Step 1. Consider feed source, feed quality, and required product quality. The design of any reverse osmosis system is based on the water specification that we expect to produce for our final products and treatment. We are aware of the high volume and quality of water purification products we need to produce daily. The volume of water required per day in Dubai is said to be specified in cubic meters per day. The membrane system design depends on the available feed water and the application. The system design information and the feed water analysis should therefore be collected first. You can also use this guideline. A. Choose feed water source such as well water with STI less than 3 and surface water STI less than 5 and etc. B. Choose overall feed water concentration in TDS or individual ions. And C. Individual ion concentration from water analysis is always preferred. Step 2. Determine the flow pattern. The standard flow configuration for a membrane system is the plug flow. In a plug flow system, the feed volume is passed once through the system. A certain fraction of the feed passes through the membrane to produce permeate. The feed is gradually concentrated and exits the system at a higher concentration. Concentrate recirculation is employed when the number of elements is too small to achieve a sufficiently high system recovery with plug flow. Concentrate recirculation systems can also be found in special applications like processed liquids and wastewater. In systems with internal concentrate recirculation, a fraction of the concentrate stream out of the module or stage is directed back to the feed side of the module or stage and mixed with the feed stream. And reverse osmosis or nanofiltration system is usually designed for continuous operation in which the operating conditions of every membrane element in the plant are constant with time as illustrated in this figure. In certain applications, when relatively small volumes of special feed waters occur discontinuously, such as wastewater or industrial process solutions, the batch operation mode is preferred. The feed water is collected in a tank and subsequently treated. The permeate is removed and the concentrate is recycled back to the tank. At the end of the batch process, a small volume of concentrate remains in the feed tank. In this mode, the operation conditions of every membrane element are changing throughout the cycle. In this mode, the operating conditions of every membrane element are changing throughout the cycle. After the resulting concentrate has been drained, The membrane are typically cleaned before the tank is filled again with a new batch. This figure shows the batch operation mode. A comparative summary of plug flow and circulation flow is given in this table. The main advantage of the recirculation concept is the defined feed flow rate to the modules regardless of the degree of fouling of parasitic modules and the changes in feed water composition. Further aspects of the recirculation concepts are mentioned in Appendix 4 and you can study it. Step 3. Select membrane and element type. Elements are selected according to feedwater salinity, feedwater fouling tendency, required rejection and energy requirements. The first factor that has to be considered is the feed source. If the feed is brackish water, BW modules must be selected. If the feed is seawater, SW modules must be considered. As an indicator, TDS for brackish water is between 1000 to 15,000 mg per liter and in seawater is bigger than 15,000 mg per liter. We will discuss it in the next slides more. Step 4. Selection of design flux. Reverse osmosis and nanofiltration systems are usually designed for a specific permeate flow rate and a specific system recovery. These numbers and the specific feed water source are the information required to estimate the number of membrane elements, pressure vessels, and states. The factor which has the greatest influence on the membrane system design is the fouling tendency of the feed water. The silt density index value of the pre-treated feed water correlates fairly well with the amount of fouling material present. The concentration of fouling materials at the membrane surface increases with increasing permeate flux and increasing element recovery. A system with high permeate flux rates is therefore likely to experience higher fouling rates, requiring more frequent chemical cleaning. A membrane system should be designed such that each element of the system operates within a range of recommended operating conditions to minimize the fouling rate and to help avoid mechanical damage. These element operating conditions are limited by the maximum recovery, maximum permeate flow rate, minimum concentrate flow rate, and maximum feed flow rate. The higher fouling tendency of the feed water, the stricter are the limits of these parameters. The proposed limits are recommended guidelines presented in this table. The average flux of the entire system, or in other words, the system permeate flow rate related to the total active membrane area of a system, is a characteristic number of a design. The design flux ranges values given in the table below are typical numbers for the majority of systems. For example, a surface water with a TDS less than 3, the design flux range is recommended between 22 to 29. Step 5. Calculation of module number. To calculate the total number of the module, this information is needed. Permeate flow in cubic meter per day, membrane active area in square meter, and design flux in liter per square meter in hour. You learned how to estimate the design flux in the previous step. You can input the minimum and maximum flux to calculate minimum and maximum number of modules. Permeate flow is determined as a given data, but membrane active area can be obtained in the membrane system design guidelines presented by manufacturers. To better understanding, I provided one of these guidelines as an example to describe it to you. After determination of the module type such as SW or BW based on the feed source and TDS, you can select the catalog. You can get some important information in the catalog such as specified performance, general product description, and product use and restrictions. Permeate flow rate can be obtained in the specified performance. For example, this module has a permeate flow of 24.6 cubic meter per day with a 99.7 salt rejection. In the test condition, you can see sodium chloride solution that sodium chloride rejection is normally specified for high pressure reverse osmosis membranes, while magnesium sulfate rejection is often specified for nanofiltration or low pressure reverse osmosis membranes. Membrane active area is also classified in the general product description, which for this module is 37.1 square meter. You can get also some information about the module such as membrane material, configuration, and feed spacer size here. In the product use and restrictions, some important information such as maximum applied pressure, maximum chlorine concentration, maximum operating temperature, pH range, maximum turbidity, maximum feed flow, and pressure drop can be obtained. Now, according to the module type and permeate flow rate, the membrane active area can be obtained, and using design flux that estimated in the previous step and this equation, the number of modules can be calculated. This catalog is also as an example for nanofiltration module, and you can get some information that you require. As I said, magnesium sulfate rejection is often specified for nanofiltration or low pressure reverse osmosis membranes. Step 6. Calculation of pressure vessel number. Total number of pressure vessel needed is equal to total number of modules divided by number of modules in a pressure vessel. The calculated number should be rounded up to the nearest integer. For large systems, 6-element vessels are standard, but vessels with up to 8 elements are available. For smaller or compact systems, shorter vessels may be selected. Small systems with only one or few elements are mostly designed with the element in series and a concentrated recirculation for maintaining the appropriate flow rate through the feed channels. Step 7. Calculation of recovery. Recovery is the ratio of permeate flow to feed water flow is calculated with this equation. With increased recovery, the pressure may increase somewhat, but the brine will be more concentrated, which can make disposal more difficult. As a matter of fact, recovery in reverse osmosis and nanofiltration is a function of salt rejection. The rejection capabilities of reverse osmosis and nanofiltration membranes are designated with either a percent salt rejection or a molecular weight cutoff value. Salt rejection is typically used for reverse osmosis membrane as this equation. Rejection is dimensionless and expressed as a fraction. CAP is concentration in the permeate and CF is concentration in feed water. Rejection can be calculated for bulk parameters such as TDS or conductivity. For membrane rating, however, rejection of a specific cell is specified. Sodium chloride rejection is normally specified for high-pressure reverse osmosis membranes, whereas magnesium sulfate rejection is often specified for nanofiltration or low-pressure reverse osmosis membranes. Let's have an example. The given data in this table are for brackish water as follows. TDS in feed water is 20,000 mg per liter, TDS in permeate 520 mg per liter, and salt rejection is 97%. Calculate the recovery. You should use the trial and error method to solve this equation. And according to this data, after calculation for this case, the recovery is 56%. Step 8. Calculation of stages. The number of stages defines how many pressure vessels in series the feed will pass through until it exits the system and is discharged as a concentrate. Every stage consists of a certain number of pressure vessels in parallel. The number of stages is a function of the plant system recovery, the number of elements per vessel, and the feed water quality. The higher system recovery and the lower feed water quality, the longer the system will be with more elements in series. For example, a system with 4 6-element vessels in the first and 2 6-element vessels in the second stage has 12 elements in series. A system with 3 stages and 4-element vessels in a 4, 3, and 2 arrangement respectively has also 12 elements in series. Typically, the number of serial element positions is linked with the system recovery and the number of stages as illustrated in the tables for brackish water systems and seawater systems. As you can see in these tables, in seawater systems, the recoveries are lower than in brackish water systems. The number of stages depends on recovery. Step 9. Determine the ratio between stages. The relation of the number of pressure vessels in subsequent stages is called the staging ratio that is represented with R. For a system with 4 vessels in the first and 2 vessels in the second stage, the staging ratio is 2:1. A 3-stage system with 4, 3, and 2 vessels in the first, second, and third stage respectively has a staging ratio of 4, 3, and 2. In brackish water systems, a staging ratio between two subsequent stages are usually close to 2:1 for 6-element vessels and less than that for shorter vessels. In two-stage seawater systems with 6-element vessels, the typical staging ratio is 3:2. The ideal staging of a system is such that each stage operates at the same fraction of the system recovery, provided that all pressure vessels contain the same number of elements. The staging ratio of a system with n stages and a system recovery can then be calculated with this equation. The number of pressure vessels in the first stage can be calculated with the staging ratio from the total number of vessels. Step 10. Balance the permeate flow rate. The permeate flow rate of the last module of a system is normally lower than the flow rate of the first elements. This is a result of the pressure drop in the feed channel and the increase of the osmotic pressure from the feed to the concentrate. Under certain conditions, the ratio of the permeate flow rate of the first element and the last element can become very high. These conditions, such as high system recovery, high feed salinity, low pressure membranes, high water temperature, and new membranes. The goal of a good design is to balance the flow rate of elements in different positions. This can be achieved by the following means: boosting the feed pressure between stages, Apply a permeate back pressure only to the first stage of a two-stage system, and hybrid system use membranes with lower water permeability in the first positions and membranes with higher water permeabilities in the last positions, such as high rejection seawater membranes in the first and high productivity seawater membranes in the second stage of a seawater reverse osmosis system. Now the steps finished. But the problem is that if you design the system according to these steps, there is a probability that the design system has an undesirable performance. Thus, it is necessary to analyze the system using concerned software such as ROSA or WAVE to fix errors. Thus, it is necessary to analyze the system using concerned software such as ROSA or WAVE to fix errors. In this course, you will learn how to design a reverse osmosis system with ROSA software, and in a separate course, WAVE will be presented. Exercise. Design the reverse osmosis desalination system according to the given data. The feed source is seawater with TDS 38,000 mg per liter, silt density index less than 3, with a 25 degrees Celsius temperature. The required quality for the permeate is also 1,200 cubic meter per liter. Required TDS is less than 250 milligram per liter with a recovery of 50%. For the design, I am going to follow the design steps as I have already discussed. According to step 1, the required permeate quality and fit analyses in these tables have specified. In the second step, the flow pattern has to determine that due to the large-scale system, plug flow configuration with a continuous flow is considered. In the third step, considering the TDS concentration, the SW module has selected. In step 4, according to the feed source that is seawater and a TDS less than 3, the design flux in the range of 13 to 17 has selected. According to this equation in the step 5 and specified data, the minimum and maximum module numbers have been calculated as you can see here. In step 6, considering the pressure vessel with 6 modules and the calculate minimum module number, 13 pressure vessels for the system have been calculated. In step 8, if you look at the table for the SW guideline with a 50% recovery, a system with 2 stages is considered. According to this data, 2 stages with 50% recovery, the ratio of 1.5 for this system has been calculated that according to the equation, 7 pressure vessels for the first stage has been calculated. In this figure, you can see an array with 2 stages designed for this exercise. Now, please do the second exercise according to the given data as well as the procedure in the next slide. Now this lecture finished. Let me know your solutions for the homework problem. You can also download it from the website. In the next lecture, we will also discuss the reverse osmosis and nanofiltration systems that how to evaluate them. Thank you for your attention.